In this video, we are going to look at the ability of certain salts to act as either acids or bases. So first, let's define what a salt is. A salt is an ionic compound that is soluble in water. And when you put a soluble ionic compound in water, it dissociates to form its component cations and anions. A couple of examples would be something like calcium nitrate. Calcium nitrate will dissociate into its ions, the calcium ion and two nitrate anions. Another would be ammonium chloride. Ammonium chloride forms the ammonium cation and the chloride ion when it dissociates. So some salts can be acidic, and what that means is that when the salt dissociates in water, the pH of the solution is lowered below 7. Also, a salt may be basic. When it dissociates, it may increase the pH of the solution above 7. A neutral salt, when it dissociates, it has no effect on the pH of the solution. So to determine if a salt is acidic, basic, or neutral, we need to look at the cations and anions that are formed when it dissociates, look at how they interact with water in order to determine if they produce hydronium ions and therefore are acidic, if they interact with water to form hydroxide ions and therefore are basic, or if they don't have any significant interaction with water. So let's start by looking at what makes a salt acidic. There are essentially three different conditions that can do that. If the salt has the ammonium ion as its cation, then it can be acidic. If the salt has a cation that is small and highly charged, such as these, it can lower the pH of the solution. Or if it has an anion that can act as a weak acid, like the bisulfate ion. So let's look at each of these individually. So if we have a salt that has the ammonium ion, it's acidic. Let's look at an example. Here we have ammonium chloride is our salt. When it dissociates into the ammonium ion and the chloride ion. Now, ammonium is a weak acid. So the ammonium ion, once it's formed, it can undergo a second reaction where the ammonium ion reacts with water and it transfers a proton to water since it's a weak acid, forming ammonia and hydronium ion. So since the hydronium ion is formed by the ammonium ion, the pH will be lowered, and therefore salts that have ammonium ion, which is a weak acid, are considered acidic salts. Secondly, salts that contain small, highly charged cations can also be acidic. The reason for this is that they interact with water and cause water to form an H3O plus ion more readily. So let's look at an example of how they do this. Here's aluminum chloride. When aluminum chloride is put in water, it dissociates to form a small, highly charged aluminum cation and the chloride ion. The aluminum cation, it's small and highly charged, and therefore in a aqueous solution, it forms very strong ion dipole interactions with water. And what that causes, let's look at this picture, it forms a complex where you have this cation, the aluminum cation, forming very strong ion dipole interactions with, in this case, 6 water molecules. The water molecules, or the electrons from the water molecules, are going to be drawn towards the very positive aluminum ion. And this weakens the bond between the water and some of the hydrogen ions. So as the electron density is pulled away from these bonds, it weakens that bond. And therefore, it allows the water to be more acidic or more likely to donate a proton to a different water molecule. So here's another water molecule. Since this proton is held on somewhat loosely, it breaks off. It's more likely to break off and be added to a different water molecule, forming the hydronium ion. So again, these small, highly charged metals, they form strong ion dipole interactions with water. We say they coordinate with water. That draws the electron density from the water molecules towards the aluminum because it's very positive. The electrons are attracted to a positive charge, weakening the bond between the oxygen and the hydrogen, making the hydrogen more likely to dissociate or come off, and that hydrogen doesn't just pop off, it is transferred to a nearby water molecule, forming hydronium, lowering the pH of the solution. And finally, a salt is considered acidic if its anion can be a weak acid. So let's look at an example here. Here we have sodium bisulfate, an ionic compound. When put into water, it dissociates to form the sodium cation and the bisulfate anion. Now this bisulfate anion, if you notice, it has a proton that can come off, and therefore that makes this bisulfate ion a weak acid. This weak acid will interact with water, forming the conjugate base, or excuse me, the conjugate acid hydronium, and therefore anytime we form hydronium, the pH of the solution will decrease. So what about basic salts? A basic salt, generally the anion is a conjugate base of a weak acid. So let's look at a couple of examples to see if we can explain what that means. Here we have an ionic compound, sodium cyanide. This dissociates to form the sodium cation and the cyanide anion. Now we need to look at the anion here, or excuse me, the cyanide ion. It can interact with water, and when it does, it could pull off a proton. When it does, it forms a weak acid. So the anion is the conjugate base that when protonated, it forms a weak acid. So therefore, if we're pulling off a proton off of water, then we increase our concentration of hydroxides. This would be my conjugate base for this dissociation reaction, and therefore the pH will increase. So let's look at a couple more examples. Let's say that we had a salt, potassium fluoride, and we put that into water and it dissociated. We would form the potassium cation and the fluoride anion. Now, we want to see if this is a basic salt, so let's take a look at the anion, the fluoride anion, and see what happens when it interacts with water, if it does. The fluoride ion, when put into water, it could potentially pull off a proton off of water. If it did, we would form hydrofluoric acid and hydroxide. Now, this is a weak acid, and weak acids do exist in aqueous solutions. So this reaction is going to occur, this interaction with the fluoride ion in water will occur, and therefore we will increase our concentration of hydroxide ions. Let's look at one other example. Let's say we had potassium chloride and we put that into water. We would again get the potassium cation and the chloride ion. Is this a basic salt? Well, let's take a look at the chloride ion in water. Now the chloride ion could potentially pull off a proton from our water, and if it did, we would form HCl and hydroxide. However, hydrochloric acid is not a weak acid. That is a strong acid, and we know that strong acids don't form, they dissociate completely. So if you put the chloride ion in water, it does not pull off a proton from water to form a strong acid. So this reaction does not happen, and so therefore potassium chloride will not affect the pH of the solution. However, potassium fluoride is a basic salt. It will increase the concentration of hydroxide because we form a weak acid, not a strong acid. And finally, a salt is neutral if it is neither, if the cation or anion are neither acidic nor basic. So as we saw in the previous example, something like potassium chloride, our cation is not ammonium. It is not a small, highly charged cation, and the anion is not a weak acid, and it does not interact with water to form a weak acid. So here, the cation is not acidic, and the anion is not acidic or basic. So this would be a neutral salt. So in general, a cation is neutral if it's from group 1A, so things like lithium, sodium, potassium ions, or if the cation is from group 2A, so calcium, strontium, barium. However, beryllium is an exception. It is what's considered a smaller, highly charged metal, so it would be acidic. So what happens if you have a salt that has an acidic cation and a basic anion? Will it make the solution acidic, basic, or neutral? Well, to answer this, we need to compare the strength of the cation, the acidic cation, and the strength of the basic anion. So we would compare the Ka of the cation to the Kb of the anion. So these values would generally be given to you. If the Ka of the cation is greater than the Kb of the anion, then our cation is more acidic than the anion is basic. So the solution would be acidic. If the Ka of the cation is less than the Kb, then the acid is weaker and the base is stronger. So we would have a net basic solution. And if the Ka and the Kb of the cation and anion respectively are equal, then our solution would be neutral